Hello, and welcome to Lesson 23 of this Introduction to Calculus with Wolfram U. The topic for this lesson is Riemann sums. So let's begin with a brief overview of the lesson. So basically there are two fundamental aspects of calculus. The first aspect is differential calculus, and that's what we've been talking about all the time so far. Now, the prime motivation over there is to find the slope of a curve at a point or the tangent line. Now, the second aspect of calculus is the so-called integral calculus, and that is what we'll cover from now on. Now, the basic motivation, the prime motivation for this part of calculus is quite simple. So basically, here's the plot of a function, and the problem is that you'd like to find this area under the curve for the function. So in this lesson, what we'll do is we'll devise a precise way of expressing this notion of area under the curve mathematically. Okay, so let's begin with some review of your earlier work. So if you have a rectangle, then its area is length times width. On the other hand, if you have a triangle, then its area is base times height over 2. But if you have a general polygon, what you would do is you'd break it up into triangles, then find the area of each one triangle, and then add them all together. Now, the area of a circle is a bit harder because it involves the number pi, but that's straightforward to work with. So question now is, what happens if you have a more general curve? So let's say you have this parabola, and you want to find the area under the parabola. How do you work it out? And to motivate the discussion, let's recall the idea of the slope at a point. So let's say if you have a differentiable function, then the slopes of the secant lines at a point will eventually approach some value m, which is the slope of the tangent at that point. So here's an example to illustrate that. You have a curve, x square, and you have a point 1, 1 on it, and you want to work out the slope at that point. So at the moment, the slope is 3.618 for the secant, but what I do now is I try and bring the point Q closer to P, and as I bring it closer, the value of the slope approaches the correct value, which is eventually 2. So that's the idea of slope at a point. You take secant lines and then you take a limit of those lines as you approach the point. So a similar idea can be used for areas, namely you break up the area into separate rectangles and then you add up all those rectangle areas and then you get an approximate area for the region. So for example, if you take the same curve and you break it up into 4 rectangles over here, then you see you get the area approximately, but of course a white space tells you that there is some error in the approximation. Now, if you take more rectangles, let's say you take 10 rectangles, you will get a better approximation, and then as you increase the number of rectangles, you will get a better and better approximation, hopefully. So that's the idea of area, which we want to explore. So let's begin now with the parabola again, and try and work with rectangles which have the top left corner at the point on the curve. And what you see over here is that in this case, you actually have an underestimation of the total area. So the answer which you get is less than the total area. So for example, in this case, your corners are at 0, 0.2, etc. And you can work out the area, then you get back the answer 0.21875. So those over here are just the function values. Okay, on the other hand, if you took the top right corner for each rectangle, then you can see you're going to overestimate the area under the curve. So in this case, you get back the answer 0.46875. So it looks like the answer would lie somewhere between 0.21875 and 0.46875. So that's the conclusion from the earlier slide, which I'm repeating over here again. So what happens as you increase the number of rectangles? Well, you see over here that as you have a larger and larger number of rectangles, then the lower and the upper estimates become closer and closer, and they are almost identical eventually. So the plots will show you what's happening over here, that as you have a larger number of rectangles, you get a better and better approximation to the area, and finally it looks like you actually get the area. But that only happens when you take a limit. So the area will approach 1/3, but that will only happen if you actually take a limit. So here's the required limit. So 1 over n is the width of each rectangle, and that's the function value, the height. So the limit over here is 1/3. That's the upper limit. And the lower limit would be to take the other end of the rectangle, and then you get back 1/3 as the answer in this case as well. Okay, so now to get a bit more general, I need to talk about so-called Riemann sums. Now this is a fairly difficult concept, so let me go slowly. So let's say you have a general function f of x, not just a parabola, and you want to work out the area under the curve between a and b. So what you do is you first break it up into n rectangles. So each rectangle will have width b minus a over n. And this quantity is called delta x. Delta means very small. So now you've broken up your interval a to b into n smaller intervals, x0 to x1, x1 to x2, etc. And the left endpoint is a, right endpoint is b. So for each subinterval, you have the endpoints given by just adding delta x every time. And so what you see over here is that the area of any one rectangle will be the width of the rectangle times the height. So let's say if you work with right-aligned rectangles, then that height will be f of x at the point xi. And so that's the total area, the sum. But if you work with left-aligned rectangles, then you get a similar sum, but with xi minus 1 as the point which you evaluate. So these sums are called Riemann sums because they were discovered by the famous German mathematician Bernhard Riemann. So here's an example which shows what's happening. You have the curve sine of x plus 2, and you want to see what happens as you increase the number of rectangles. So let's play the animation. And you see that you get a better and better approximation as you increase the number of rectangles. But of course, things are not so simple because at some cases, some places you get a slightly smaller area, and at some others you overestimate the area. Okay, so now we can make a formal definition of the area. So the area under a curve is defined to be the limit of the sum of the areas of the rectangles. Now that's the case for right aligned because you're working with f at xi, but if you want left aligned rectangles, then you get almost the same expression, but now you start at 0 rather than starting at 1. Now the fact is that if your function f is continuous, then both those limits will exist, and in fact they'll be equal. So you could work with those sums, or you could actually take the values at any number in the subinterval for each I. And these numbers are called sample points. So in particular, if you have right aligned triangles, then you have the sample points xi, and if you have left aligned rectangles, then you have the sample points xi minus 1. So that's the general formula for the area with any sample points for each subinterval. So for example, here I've taken the sample points to be the midpoints of each subinterval. Okay, so now it's time to work out an example. So let's try and work out the area of sine x from 0 to b, where the number b lies between 0 and pi. So here's a plot. Now we break up the interval into n subintervals, work with, let's say, right-aligned rectangles, and you get the answer for the area as 1 minus cosine b. But of course, you could then replace the b with pi, and you get back a much nicer answer, which is just 2. So that's the power of the whole method, namely it gives the exact answer under this curve between, in this case, 0 and pi. Okay, so now a slightly more practical problem. So let's say a car moves on highway, and you're given the velocities at different times at 10-minute intervals, and you want to work out the total distance covered in 100 minutes. So what you do is you divide by 60 over here. After all, you want to work with minutes, and you take the height, so to speak, as velocities. So you take 63, 62, 61, etc. from here, and you get back the sum, which is just the distance covered. But you could also take the heights to be the velocities at the right endpoints, like I've done over here, in which case you get back the answer 108.33. So that's a plot of the velocities, and we worked out distance in two ways, using the left values and the right values. But of course, you could be more precise and assume that the velocity is given by a certain function, in which case you could work out the distance by a similar method as early on. You take a limit of a sum, and the velocities must be then found out at those values over here, and then you get back the answer as 109.394 in this case. So that's a plot of velocity, and the area under the curve in this case will give you the distance covered in that interval of time. So that brings me to the end of this lesson. So basically, finding areas is a very practical matter. You've done it forever, so to speak, from, let's say, middle school all the way up. But to work out the area under a general curve, you must divide into rectangles and then add those areas up. And finally, we are doing calculus, so you must take a limit as those rectangle numbers approach infinity, and then you get the real area under the curve. Now, these sums which you compute are called Riemann sums, in honor of the mathematician Riemann. And these Riemann sums can also be used to work out the total distance traveled when you're given only the velocity. So that's the end of this lesson, and the next lesson we'll talk about Riemann sums in more detail. But before doing that, there'll be a problem session which you'd certainly look at and understand the topic in much greater detail. So thank you very much. I'll stop over here.